This decomposition into irreducible subspaces or matrices which are invariant under shift operation, under choice of origin, so-called cyclic matrices or Toeplitz matrices, is so common in physics because so often we assume that space is homogeneous and isotropic that it has a name of a French mathematician or physicist who invented it to study propagation of heat. So invented it for some reason. It has nothing to do with our discrete lattices, but it turns out to be extremely powerful. And the operation of going from our configuration lattice coordinates, the original place 0, 1, 2, 3 in a spatial or spatio-temporal discrete lattice, to the space of eigenvalues and eigenvectors has a name. It's called discrete Fourier transform. If you have a lattice state, phi, meaning it's a set of values of the field on lattice side 0, 1, and lattice sides, and that lattice is periodic, so it's natural to use this method. Then kth Fourier mode, let's say coefficient, is a projection of this vector in the n-dimensional space on eigenvector pointing in that space in fk eigenvector direction. For example, when we did it for two lattice sites, we started with Cartesian coordinates x and y, but it turned out the natural coordinates for translation operator being the eigenvector translation happened to be diagonal, so one was going this way and the other one was going that way. Now when you have n sites, there's more to it, but it's not a big deal. It's really just all related to eigenvalues being on a unit circle and eigenvectors being constructed for them in a very simple way. You take your state. I come with my eigenvector in a kth direction. I dot it with Hermitian conjugate. And I call the number, this will return two vectors dotted, just return a number. This number will be called kth Fourier component, which is 1 over square root of n. This eigenvector just has roots of unities as its components. Remember, it's the prime root of unity is 2p to the n. The kth eigenvector had a k here. And then I have to sum up. It had coefficients from 0 to last one, so I have to sum out over those guys. And this is an eigenvector with, this is just any vector without component. And now when you look at it, you have always been already exposed to Fourier transforms. Usually you taught them immediately in continuum, so instead of having this discrete sum, this is an integral, but the phase looks like that. There's some phase number and there is something that's called x, meaning configuration, but remember now configuration is integer points along x-axis. And L is called, often in physics gets interpreted as a momentum. You've seen lots of things that you saw I x times p integral continuum of the functional continuum. And you just know that and you do it. Now I prefer to understand it first in a discrete setting, in discrete Fourier transform, because these are just matrices. You know what you're doing all the time, and everything is finite and computable. So these are just complex phases. They're there because they're eigenvalues of the translation operator. And the sum says you take components of the vector and you sum them weighted by this complex number. So the simplest example is if k equals 0, then all the components are the same. And what this thing says is take a vector and sum all of its components and divide by square root of n. If you're dividing by n, you would just be computing average value of vector component. But it turns out for normalization purposes, square root n is correct thing to do. If you take any other non-zero k, then what happens is these phases run on a complex circle. They have different components in this space and that space. You can write them as cosines and sines. So they're all weighted averages of components, and they'll have the property that they're on the orthonormal spaces. So this is a projection from your original Cartesian coordinates x1, x2, x3 to new Cartesian coordinates, let's say momentum 1, 2, 3. But everybody is still orthogonal. It's a nice representation. But any function of the translation operator, or anything the commutes translation operator, collapses to a number instead of being homologous matrix. So that's why I'm teaching you that. And here is an application that we often see. I'll do that as next clip.